In the previous video, we learned that if we have a slit of finite wave, what happens is the wavefront that managed to pass through a slit, every element of area of that wavefront will serve as a source of secondary wavelets. So there will be plenty of secondary wavelets overlapping in this region here, and interference of many waves together, we call it as diffraction. So this diffraction is very complicated over here, but if you place a screen over here, I can simplify it and let you know that what you can observe on the screen will be something like this. Okay, I'm not able to prove it to you as easily as interference from last time, but yeah, if you put the screen somewhere, this is the kind of pattern that you'll be observing. Okay, the pattern is it's similar to the interference of double slits experiment, but also quite different. Okay, there are some defining characteristics that you need to notice here if you compare it with the interference experiment. So one thing that you should notice is that not all of the bright fringes have the same brightness. You can see that the central bright over here is very high intensity of its light, but afterwards you see that the intensity drops severely for the next few bright fringes. So you can see that if you look at this stripe over here, you can see that the central bright fringe is very bright, it's very white. But after that, you see that the next bright fringe is actually slightly dimmer. Then it gets dimmer and dimmer as you goes on away from the central bright. So the brightness will decrease for the other fringes outside of the central bright. So that's one of the defining characteristics for a diffraction pattern. And also another thing that we can talk about for diffraction pattern is that if you notice here, the central bright over here, it's twice the thickness of the other bright fringe that you see outwards. Okay, you can see the central bright, it's much thicker compared to the next bright fringe, next bright fringe, next bright fringe. And actually, if you try to do it through calculation, you can see that the central bright is actually 2 times the width of the other bright fringe that you see here. Okay, for interference, it's not the same. Interference, all the bright and dark fringe have the same width. The central bright and the first bright and the second bright and the third bright and the fourth bright, all of them have the same width. Same for the dark fringes, they all have the same width as well. But when we talk about diffraction by a single slit, the central bright will be twice the thickness of the other fringes that you see away from the central bright, and also the brightness will get dimmer and dimmer as you go away from the central bright. Okay, so 2 defining characteristics that separates the pattern for interference of double slits pattern and diffraction by a single slit pattern. Okay, so that's the main difference in their characteristics, qualitative differences. Now let's move on to talk about the equation that we can derive for diffraction. Okay, we are going to go through a similar process just like what we did for interference of double slits, but instead of focusing on the points where we see bright fringes first, followed by the dark fringes, like what we did for interference, for here we are going to focus on the point where destructive interference happened. Okay, because technically for the diffraction experiment, right, it is the diffraction that caused the dark fringes, and those places that I should clear my words. It is the destructive interference that causes these dark fringes to occur very clearly. But other places you see some amount of brightness is not because they are fully constructive interference, but because they are not fully destructive. Okay, it might be a bit weird to say this, but I can think of it as this central bright here, it's fully constructive, correct? But this first dark over here that you see here is fully destructive. All of the light wave over here will cancel out when they reach here. Okay, that's why it's a dark fringe. There's no light over there. But afterward, you see a bright fringe, but it's not so bright, right? Okay, not so bright. Why? It's because even though it seems like a constructive interference, but it is not fully constructive. It is only partially constructive. Some of the waves still cancel each other out as well, so it gets dimmer. Okay, and when you get further outside, the wave that overlaps constructively is very minimal already. The majority of the wave actually cancel each other out, so it gets even dimmer. It gets even dimmer outwards. Okay, so it is the destructive interference that is the key in causing this black fringes that the dark fringes that you see here. The other bright spots that you see here are actually just not managed to fully destructive. Okay, it's not because it's fully constructive, it's just that it is not being able to be fully destructive. That's why there's still some amount of color that you can see here. Okay, but no matter what, we are going to start by deriving the equation for destructive interference first. Then afterwards, we can try to think about how about these bright fringes, how can we think about it. So let's start with the destructive interference. So we are going to create an equation. Again, we are going to relate between a few measurable things. So the first measurable things is the length or the width of this slit over here. Again, this is a slit of finite width, so the width of the slit can be measured. In the interference experiment, our double slit experiment, those two slits are narrow, so we almost assume that the width of the slit is negligible, it's very narrow. But now we are going to assume it to be finite. So finite means that you are able to measure the width of the slit. Okay, D is still the same capital D over here. It means the distance between the finite width slit over here and also the screen over here. It still represent the same thing. And also you have Y, the same Y. Y is the distance of a particular fringe from the central bright. Okay, from the central bright, if you measure upwards or measure downwards to the fringe that you are interested in, how much distance is it? That is Y. Okay, so we know that over here destructive interference occur because you see a dark spot over here or a dark fringe over here, so definitely destructive interference. You know from destructive interference, their defining characteristics is that their path difference is something plus half lambda. Okay, so a standard one will be 0.5 lambda. Okay, so what happened here is which wave destruct which wave, okay, or which wave interfere destructively with which wave. Right now I'm only illustrating 8 dots over here, right? There are only 8 sources over here. Okay, there are plenty, there are thousands that I can draw over here, but for simplification purposes, I'm drawing 8 dots only. So which dot will cancel out which dot? Okay, that's the thing that we want to tackle right now when we talk about destructive interference. We know that they should all cancel out. Which are all 8 sources over here, they produce their own secondary wavelets, right? All 8 sources here will cancel each other out eventually. But now we need to think which area or which spot or which dot cancel out which dot. Okay, that's what we want to think about. And for the first fringe, for the first dark fringe that we see over here, it is the first dot over here and the 5th dot over here that cancel each other out. Basically, we are going to split our slit into 2 halves, the upper half and the lower half. The upper half will cancel out the lower half. So your red will cancel out the red over here. Okay, later I will tell you also the second one will cancel out the 6th dot, the 3rd dot will cancel out the 7th dot, the 4th dot will cancel out the 8th dot. So it's basically half-half. The upper half will cancel out the lower half. That's the idea how you get the first dark fringe over here. But later we'll talk about the detail. Okay, so we are going to call this as A over 2 because we are splitting it to upper half and lower half, right? So the distance between the upper first dot and the lower half first dot over here is A over 2, half of the width of the slit. Okay, so we are going to draw the same 2 lines. So this one will be R1, this one will be R2 as usual. So R2 minus R1 is going to be equals to A over 2 sine theta. If you ask me where do you get this A over 2 sine theta, you might need to review back to the interference video that we did last time. In the interference video, do you remember I labeled, oh, here is theta, then here is 90 minus theta, then here is 90 minus theta, therefore here is theta. Then after that, I draw for you a triangle and I show that how you resolve it. Then you find R2 minus R1 is where it is still exactly the same thing. So from that, last time this thing over here, last time this distance over here is the distance between the 2 slits. But right now, this distance over here is half of the width of the slit. So last time it was D sine theta, but right now it's A over 2 sine theta. Okay, if you wish to understand the why do I get A over 2 sine theta clearly, you will need to revisit the interference video to see how we derive the D sine theta over here. If you understand the D sine theta, well, last time it was just D sine, last time it was D over here, now it's A over 2 over here. It's still the same idea. Okay, so A over 2 sine theta will be equals to 0.5 lambda. We are just combining the 2 equations over here. Then it's still the same thing as interference derivation that we did last time. We're going to do a small angle approximation. Small angle approximation will cause sine theta over here to be substituted with tangent theta. Then y tangent theta can be replaced with y over d. You have to revisit that same video that I mentioned earlier. I'll probably pop a link up above somewhere here. Okay, but basically you can refer to that derivation to understand why this tangent theta can be replaced with y over d. Okay, we see there's a few approximation that we're doing there, but if you watch the video, I think you'll be clear with it. Okay, so now if you rearrange it, we'll get y is equal to lambda d over a. So this distance here, y, can be expressed using the wavelength of the light that is passing through the slit, multiplied by the distance between the slit and the screen, divided by the width of the slit. Then you're able to get this y over here. Okay, so the red point here will disrupt the red point over here. They will interfere destructively. Then the orange point here, if you draw a line over here, the orange point here, you draw a line over here, you get that R2 minus R1 should be the same thing also, which is 0.5 lambda. Okay, if you think about it, I think it makes sense. Okay, because you go down by a little, this one also will go down by a little, so the length over here will be similar to the length over here. The length over here will be similar to the length over here, so the difference will be the same, which is 0.5 lambda. Okay, so red cancel red, orange cancel orange, green cancel green, blue cancel blue. So at the end, everything cancel out, so none of the light that reach here will survive. All of them will interfere destructively. That's why there's a dark area over here, because there's no light that survive the cancel thing. Okay, so that's for the first dark fringe. We can proceed to the second dark fringe and try to understand what happened. Well, it's basically the same idea. A little bit of tweak will be, right now, instead of splitting it into an upper half and a lower half, we are going to split it into 4 parts instead. So part 1 will be the first quarter of the slit, part 2 will be the second quarter of the slit, the third quarter of the slit, and the fourth quarter of the slit. We're going to split the slit into 4 parts. So right now the first dot will cancel out the third dot. Then I think you can think about it. The second dot will cancel out the fourth dot. The fifth dot will cancel out the seventh dot. The sixth dot will cancel out the eighth dot. So at the end, everything cancels as well. That's why here there's a dark spot as well, the dark fringe over here. Okay, but right now this one is definitely closer. And I believe you know that this distance here is a over 4, because I say you split into 4 parts, right? So this one is a over 4. So right now, R2 minus R1 will be a over 4 sine theta. Okay, a over 4 sine theta. So if you go through the same process, bring everything here, do small angle approximation, change it with y over d, you get y is equal to 2 lambda d over a. So just now it was 1 lambda d over a for the first dark fringe over here. For the second dark fringe, you get 2 lambda d over a. Okay, so the same idea will continue to apply. Okay, so red cancel red, green cancel green, blue cancel blue, orange cancel orange. So basically everything should form a pair and they should cancel each other out. That's why we always split in even number. We split to 2, we split to 4. We never split to 3. Okay, we split to 2, we split to 4, because it's always even number, then everyone can find a pair, only they can cancel each other out. Okay, we are now moving on to the third dark fringe over here. Basically the idea is still the same, but now you might be thinking, I already split to 4, how can I split to 8? Well, how do I split further? Or split to 6, how do I do it? Well, yeah, I cannot do it here. It's because I only put in 8 dots over here. But let's exaggerate the slit width a little bit. Let's exaggerate by making the slit a bit larger. Then we replace it with many dots. Okay, I'm not saying that we expand the slit. I'm just saying that we zoom in to look at the slit. If we zoom in, now the slit appears to be larger, right? Okay, we are looking at it from a closer view. So now we can put in more dots inside. Okay, but it's still the same width of slit. We are not making the width, we are not making the hole larger. We're just looking closer to the hole so that the hole appears to be larger in our eyes. So now we can put more elements of area inside it, or we can put more points inside it, or you can put more dots inside it. So now if you refer back to the same idea, the first dark fringe you split into upper half and lower half. Red cancel red, orange cancel orange, yellow cancel yellow, green cancel green, blue cancel blue, dark blue cancel dark blue, dark blue cancel dark blue, purple, okay, you get the idea. So basically we can still split into even more points, it's still the upper half cancel out the lower half. That's for the first dark fringe. Okay, so that's why it's A/2 for the distance between the pairs. Okay, we derived this already. Next, for the second dark fringe, we are going to split into 4 parts. So you have your first quarter, second quarter, third quarter, and fourth quarter. So they will cancel out by pairs as usual. Red cancel red, orange cancel orange, yellow cancel yellow, green cancel green, blue cancel blue, purple cancel purple. It works for the first 2 quarters. It also works for the third and fourth quarter. They should cancel each other out as well. So at the end, everyone find their own pair. They cancel each other out. Nothing arrive at the second dark fringe. And we go through a derivation already. This time this is A/4. So you go through a derivation and get 2 lambda d/A. Okay, it's still the same thing. I'm not making no changes to it. I'm just making more points in the slit so that we can see more clearly how they cancel each other out. Okay, and I put in more points because it allows me to explain the third dark fringe as well. For the third dark fringe, what happened is I'm going to split into 6 halves. So you have a first half, second half, third half, not 6 half, 6 part. First part, second part, third part, fourth part, fifth part, sixth part. So now you can see that it's A/6 right now. So you go through a derivation, you get 3 lambda d/A. Okay, this is 3 lambda d/A. So how do they cancel out? Well, all the reds will cancel out. Red cancel out, red cancel out. Basically this one cancel this one, this one cancel this one, this one cancel this one. Green cancel green, green cancel green, green cancel green. So everybody find their pair, they also cancel out. Okay, but right now the distance between the source that cancel out becomes closer and closer. Okay, the distance between the 2 sources that are supposed to cancel out, the pair that are supposed to cancel out, the distance between them gets shorter and shorter. Okay, so I believe for the fourth one, it's still the same idea. We split into 8 parts. 1, 2, 3, 4, 5, 6, 7, 8. So red cancel red, blue cancel blue, green cancel green. Same idea, red cancel red, blue cancel blue, green cancel green. So at the end, everybody find their pair, nothing reach here. So it's a dark fringe as well. Go through the derivation. This one is getting the slit A divided into 8 parts, right? So A divided by 8. So if you go through the derivation, you get 4 lambda d/A. So this one will be y4 is equal to 4 lambda d/A. Okay, so I believe it's a clear trend that you can observe over here. So I'm going to make generalize it into an equation. So for dark fringes, we can generalize it to become y is equal to m lambda d/A. Okay, so you can see that this was the equation for constructive interference in interference. But right now for diffraction, it becomes the dark fringe equation. Okay, last time m lambda d/D was for bright, but now m lambda d/A is for dark. Okay, so if you want to think about it, there's one important thing that you should think about is whether we can put 0 in or not. Okay, if you substitute m is equal to 0, you get y is equal to 0, right? Y is equal to 0 means there's no distance from central. So if no distance from central, it's a dark. Does it make sense or not? No. The central, it's a bright. It is not a dark. So if you put 0 inside, you get y is equal to 0. That is not valid. So that means for this equation here, how is it special is your m cannot allow substitution of 0. Because if you substitute 0, y is equal to 0, you're saying that y is equal to 0 is a dark fringe. But it's not true. Y is equal to 0 is actually a bright region. So therefore, you are not allowed to substitute m is equal to 0 for dark fringe over here. They always start with 1, 2, and 3. Of course, you have positive and negative, but like I said earlier, we don't really care much about it. We're still up and down us. We are not focusing on whether it's above or below the central bright. Okay, so now we understand dark fringe. We are going to make some kind of assumption. Okay, we are going to assume that the bright fringes are situated right in the middle between the dark fringes. It is sort of a logical kind of assumption. So if there's dark over here, there's dark over here, in the middle between 2 dark must be a bright, right? Because you see it's alternating. So if there's dark here, there's dark here, in the middle there will be bright. Okay, it's something quite logical to understand. So if you understand this logic behind here, you know that if this is 1 lambda d over d, 1 lambda d over a, this is 2 lambda d over a, in the middle of it, it'll be 1.5 lambda d over a. In the middle over here, it'll be 2.5 lambda d over a. In the middle over here, it'll be 3.5 lambda d over a. So you know that the equation for bright fringe will be just like this: 1.5, 2.5, 3.5. You don't need to derive about it. You don't need to spend too much time to derive it. Just think about it. The bright should be in the middle between two dark. Okay, so if you know the dark equation are like this, the bright equation is just in the middle of it. Between 1 and 2 is 1.5. Between 2 and 3 is 2.5. Between 3 and 4 is 3.5. So now the equation for bright fringes will be m plus half lambda d over a. So this is similar to the destructive interference equation in the double slit experiment. But now, last time for interference, this equation is for dark. But now in diffraction, this equation is for bright. Okay, of course they differ. In interference, this is d, the distance between the two slits. But in diffraction, this is a, which is the width of that one single slit. Okay, again, m over here, because you cannot substitute 0, so the same thing over here, you are not allowed to substitute 0 over here. It starts with m is equals to 1. If you think about it, why you cannot substitute 0? Because if you substitute 0, it will be 0.5. 0.5 is less than 1. So it means that it's somewhere around here. Somewhere around here is definitely not the region where you have your bright fringe. Your bright fringe is somewhere here. So it should be 0, jump to 1. It should be no equation for the central bright over here. It starts from the first dark onwards, only you have equation. So m, you are not allowed to substitute 0 for diffraction. So it will be 1.5, 2.5, 3.5. There's no 0.5 over here. Okay, so you have the equation for dark fringe, you have the equation for bright fringe. Okay, so right now let's try to summarize everything in this diffraction pattern over here. I'm going to continue with the naming of it. How do you name all these things? Again, it's still the same thing. These are m, right? So if these are m, then your mth order dark fringe, if you have the word order, then 1 will be referring to the m over here. The number of the order number, the order number is 1, so this is first order. The order number is 2, so this is 2 lambda d over a. The order number is 3, so this is 3 lambda d over a. The order number is 4, so this is 4 lambda d over a. So for this one is 3 plus half, right? 3 plus half. So 3 plus half means that m is 3, therefore it's third order. So it's 2 plus half, so 2 second order. This is 1.5, this is 1 plus half, 1 first order. Okay, so for order, you just refer what m do you substitute inside, and then that will be the number for its order. Okay, again, if you don't have the word order, you have to count beyond or outside the central bright. This is the first time I see a dark fringe, second time I see a dark fringe, third time I see a dark fringe. So this is the first time I see a dark fringe, so this is first dark fringe. Second time I see a dark fringe, second dark fringe. Third time I see a dark fringe, third dark fringe. Fourth time I see a dark fringe, fourth dark fringe. Okay, so for the names that doesn't have the word order, you have to count out of the central bright, which is the first time, second time, third time, fourth time I see it. If there's the word order, then you need to know what is the value of m that you need to substitute, then that value will be the value put in front of the word order. Okay, so you can refer to the to the whole table over here to understand everything clearly. Okay, but before we finish the explanation, okay, I'm actually done with the explanation for diffraction. There's a little bit of caveat that I want to say. Okay, just I make some kind of assumption. I say that assume that the bright are situated right in the middle between the dark, right? It's not exactly true, actually. Okay, it is an okay assumption to assume that the bright is right in the exact middle. But if you do the experiment, if you read university books, it's actually slightly debated. That means that the bright is not exactly in the middle between two dark. It can be slightly to the left, it can be slightly to the right. The equation is much more complicated than what I'm showing here. Okay, for diffraction, usually it's the dark fringe equation that we emphasize on. It's not usually the bright that we emphasize on. Okay, if you read university book, they are usually focusing on the place where dark fringe occur. Okay, because the bright fringes are not exactly constructive. The bright fringes are actually just remainder of the light that does not cancel off. Okay, the remaining light that does not interfere destructively will appear as bright. is not because it's constructive. So we don't really place too much emphasis on it. So all these equations that you see on the left over here, they are just approximation. It's good enough for our understanding, but it's not exactly true. But I think it is okay to just write it like this, because what for do we need to know the exact position of bright fringe? Because there's no meaning to it. It's not constructive interference. There's nothing we want to study there. It's just light that didn't manage to cancel each other out. Okay, so you can just hold on to what we have discussed over here for our syllabus. Nothing to worry about. So again, the naming is very important. Please make sure you see the word, whether the word order exists in your question or not, in order to solve this question. If there's a word order, that is the M. If there's no word order over there, you need to count carefully. Okay, so that's it for my explanation for diffraction. Thank you. Diffraction by a single slit. Thank you very much.